Hi class, in this video I'm going to go over one more optimization problem. It's a kind of problem that shows up on the WebAssign, but we didn't really get to an example like this in class. So in this problem we're going to find the global max and min of this function f of xy equals x minus y on the region described below, where x squared plus y squared is less than or equal to 9 and y is greater than or equal to 0. I'm going to preface this by saying that this is a more complicated example than anything I would give you on the quiz, but since it shows up on the homework, I thought it'd be good to put this video out. Let's start by drawing the region so we know what we're up against. So we're supposed to be inside the circle of radius 9 centered at the origin and above the line y equals 0. So that's this region right here. As usual, we want to think through sort of the three possibilities of where the global extrema might show up. So the global max and min might be at critical points of the function. That would be if they're on the interior of this region in the light green shaded part. They might be on the boundary, or there might just not be a global max and a global min. Now, since this region is closed, it includes its own boundary, and it's bounded, does not extend infinitely far in any direction, we can eliminate the last possibility. So now I'm going to sort of go through the first possibility and see if we can find any critical points of this function. So critical points are where the gradient equals 0. So I'll calculate the gradient of the function f of xy, and we see that it's just the vector 1, negative 1. In particular, this vector is never equal to the 0 vector. So critical points are where the gradient equals 0. So this must show us that there are no critical points. So we've now narrowed ourselves down to global extrema have to be on the boundary. Now the boundary sort of has a few parts. It consists of the half of a circle. It has the line segment along the y-axis. And let me go ahead and write down the equations for these things. The equation for that top half of the circle is x squared plus y squared equals 9. And that line segment on the bottom is the x-axis, so where y equals 0. Now there's one more part of the boundary that we didn't really talk about in class, and that's the endpoints, where the line segment and the half circle meet. Think of these as the boundary of the boundary. The reason I say that is that if you think of the line segment as being one of the places that we're going to look for possible global maxes and global mins, that line segment itself has a boundary. The boundary of a line segment is its two endpoints. And so we really do need to check those separately. So I'll go ahead and go through these three parts of the boundary sort of one at a time, starting with the top half of the circle. Now this is a constrained optimization problem, so I'm going to need to write that circle as the level set of some function. So here I think it makes sense to use the function g of xy equals x squared plus y squared, and then that top half of the circle is the curve where g equals 9. Now the Lagrange equations, as we know, are that the gradient of f is a scalar multiple of the gradient of g, and that g equals 9, the constraint. So let me write these out. Gradient of f we already figured out, and the gradient of g we can figure out pretty quickly is 2x comma 2y. And then g equals 9 is just the original constraint equation that x squared plus y squared equals 9. Now remembering that that first equation with the vectors I can really write down as two separate equations. That the x components are equal is that 1 equals lambda times 2x. The second one is going to be that negative 1 equals lambda times 2y, and then of course the constraint. Now I'll do a little bit of algebra to see if I can figure out what the points x, y that satisfy all of this are. One thing that we often do in algebra when we're solving a system of equations is solve for one of the variables in one of the equations, then plug it in. So solving the first equation for lambda, I get lambda equals 1 over 2x, and I'll plug that into the second equation. And then just doing a little bit of algebra here, I see that negative 1 equals y over x, or that y equals negative x. Now I can go ahead and plug that into the last equation, into the constraint, and we'll see that that's really x squared plus, I guess, negative x squared equals 9. So the nice thing about this is I finally have an equation with just one variable. So solving for x, I'll skip a couple steps here and realize that x is equal to plus or minus 3 over root 2. So this is really two solutions for x. That x is either positive 3 over root 2 or x is negative root 3 over root 2. And I'll figure each one of these out separately. And as I did in class, I'll sort of draw a line to separate my work for each of them. Well, since y equals negative x, each of these is pretty easy to find the point for. So I can get the point 3 over root 2 comma negative 3 over root 2. And then I get so the negative of each of x and y for the other possibility. So I ended up with 2 points as solutions to this system of equations, to the Lagrange equation. So these are my two constrained critical points along the semicircular piece of the boundary. Let's go back to the picture so we can see where these points are along the curve. So I'll draw the first point, which is where x is negative 3 over root 2, and y is positive 3 over root 2. It's about here. But then we realize the other point is along the circle. It's along the circle where x squared plus y squared equals 9, but it's not along this semicircle, so I don't actually need to include it. So I'll go ahead and eliminate that one from consideration. Now let's think about the line segment. The equation for the line segment is y equals 0, and so we can use the Lagrange multipliers here again by just saying g of xy equals y. Then the line is where y equals 0, so where g equals 0. Again, I'll write down the Lagrange equations, and we'll see if we can find any solutions. So once again, the gradient of f was 1, negative 1. And if we figure out the gradient of g, we'll see that it was 0, 1. So if we look at the x components of that first equation, we realize that it's saying that 1 equals lambda times 0, which of course isn't possible. And so if one of the equations can't be satisfied, that means there must be no solutions to the system. So there's no Lagrange points along this line. And so that takes us to the third thing we need to check, which is the endpoints of the line segment, which are the same as the endpoints of that semicircle. And so these occurred at the points 3, 0 and negative 3, 0, which we can see once we go back and look at the picture. So I'll mark those points as well and label them 3, 0 and negative 3, 0. And we realize that there are 3 sort of candidate points for the global max and the global min. Again, we know that the global extrema have to be on the boundary because we eliminated the other possibilities. So the global max must be one of these 3 points and the global min must be one of these 3 points. So now to check which is the global max and which is the global min, it's just a matter of plugging them all into the function f and seeing which one has the greatest value, that must be the global max, and which one has the least value, that must be the global min. So I'll go ahead and do that for each of the 3 points. And once I have those values, I might need to check and see exactly what 6 over root 2 is equal to. That is actually less than negative 3. And so the least one is at that point negative 3 over root 2 comma 3 over root 2, so that must be the global min. And the greatest one occurs at the point 3, 0, so that one must be the global max. So now let's see if we can make sense of that intuitively. Remember what the function was. It was f of xy equals x minus y. So you would assume that this would be maximized when x is large and y is small. So x being large means we're over to the right, y being small means we're as low as possible. It makes sense that the maximum would occur at the point 3, 0. If we're trying to find the lowest value, we'd want x to be as low as possible and y to be as great as possible. So it makes sense that up here, somewhere around here, would be the global minimum. And so as we found the global max ended up being at one of the endpoints, and that the global min ended up being along one of the boundary curves.